Momentum and rotation, review 6. The figure shows an overhead view of a rod, which has been nailed downward at one end into a frictionless tabletop. A mass of clay slides on the table, approaching the rod. When the two collide, the clay sticks and the combined mass rotates. We're up above, we're at the ceiling, and we're looking down on this. And we have a rod that is attached with a nail to this frictionless tabletop. And we see this blob of clay sliding along the table, and it's going to run into the rod here, and it's going to stick. Question 1, what type of collision is that? It is a perfectly inelastic collision, or totally inelastic, or completely, something like that. Any of those terms are fine. Linear and angular momentum are conserved in such a collision, but mechanical energy is not. So we are definitely not going to use conservation of energy to solve this. In fact, I think we're going to use conservation of angular momentum, because we're going to have some rotating that happens with this rod after this collision, and so it's most convenient to use angular momentum. We want to determine the angular speed of the combined mass just after impact. Angular speed is omega, and we remember a couple of equations for angular momentum. One is that angular momentum is the moment of inertia multiplied by the angular velocity. Another one is for a mass that's moving in a straight line, mv r perpendicular. Even a straight moving mass, like this one right here before it hits the rod, can be considered to have angular momentum about some particular point. So let's conserve angular momentum here. The initial angular momentum needs to equal the final angular momentum. Initially, the angular momentum is due entirely to this 3 kilogram mass, and we're going to use this equation right here. 3 kilograms times a speed of 6 meters per second, and r perpendicular is 2. On the right side here, now we're going to have rotating things, and we're going to go I times omega. Now omega is what we're looking for. What about I? What's I? I is the moment of inertia of this combined mass, which is the rod plus the moment of inertia of this thing, plus the moment of inertia output of the 3 kilogram mass. For a point mass, the moment of inertia is mr squared. A rod like this, we could look this up, that is rotating about its end has a moment of inertia of 1/3 ml squared. And that whole thing needs to be multiplied by omega. So let's see if we can put some numbers in here. On the left side, this is going to be 36. And then I'll put the omega in front here. Is that okay? Put the omega in front. And then what have we got here? This is 1/3. The mass of the rod is given as 2. The length of the rod is given as 3. So we've got to square that. And then for the point mass, it has a mass of 3, and it's going to be 2 meters away from the rotational axis. What does this come out to be? This is going to be 6, and that's going to be 12, so that's 18. So I think omega is going to be 2 radians per second. Last part, determine the thermal energy generated during the collision. With thermal energy, we need to consider what's the initial kinetic energy and what's the final kinetic energy. So let's go back to the picture here quickly, and then we'll roll back down. Initially, this mass here is the only one that has kinetic energy. So that's going to be 1/2 times 3 times 6 squared. 1/2 times 3 times 6 squared. And what does that come out to be? That comes out to be 54 joules. That's how much kinetic energy we have to start with. At the end, I sure hope we have less. Now, this system is rotating, which means its kinetic energy is 1/2 I omega squared. 1/2. We decided that the moment of inertia, you see this thing in brackets, we decided that that was 18. So that goes right there. And omega we decided to be 2. So what does that come out to? 36. So how much thermal energy was generated? Subtract those two. About 18 joules.